start. Welcome everyone to this afternoon's session on formal QFTs. And this afternoon, we're very happy to have as our first session speaker, Congkao Wen from Queen Mary University of London. And he will be speaking about modularity and n equals 4 super Yang mills and superstring theory. Please take it away. Let's test for it.
Hi, is it on now? Sorry. Right, so yeah, let me just continue. So as I was saying, under S transformation, well, you change the coupling, but you also change the gauge group, where GL denotes the so-called Lagrange dual. So here I give you some examples that will be relevant for this talk. Well, if you saw the so-called Lagrange dual group before, so you may notice there are some global structures. But for the observable, I will be considering, so we will not see those global structures. So therefore, I just list the relation of algebra. Okay. Yeah. Oh, SP dual to SP. No, I mean SP related to. Okay, I didn't know that, but okay. Okay, thanks. Right, there are also like exceptional group. Actually, people also work on exceptional group as well in this content. But this talk I will just focus on the classical groups. So you see that say for SUN, the gauge group does not change once again. So up to this global structure, which will be sort of irrelevant for the observable, I will discuss. But in the case of USP, as Ami mentioned, But in this case, USB will change to a SO2m plus 1. So the statement of S-duality is that the physical observable should follow those rules. And the observable we will discuss as a correlation function of local operators. That's right, yeah, yeah. Another reason, and for superyamus, people are interested in it, also appears in many other talks because of ADS-CFT correspondence. So, yeah, this I think appear many times that and for superyamus, people believe that should be equivalent to type 2B superstring theory on ADS5 cross S5, and the physical observable, namely correlation function, which we will study here in for superyamus, should be related to the scattering amplitude of, say, quantum gravity, in this case, type 2B superstring theory on ADS5 cross S5. Okay? If you attended the, say, Chichester talk, that was the property he used to do the bootstrap. You may also know that type 2B string theory also enjoy S-duality. So therefore, you know, the S-duality of N for superyamus is, according to ADS-CFT, is mapped to S-duality of a type 2B string theory. So here I just write out the mapping between the, say, field theory parameters and the string theory parameter. So in particular, the Yamus coupling, or complexified Yamus coupling, is mapped to the string coupling. So in string theory, as you know, that the coupling is given by expectation value of scalars. So in this case, where chi is the axiom and the G string, the string coupling is associated with the expectation value of dilettone. ADS5 cross S5 has a radius, and this radius is related to, well, the rank of the gauge group. Here I call M. So alpha pi is the square of the string length. So therefore, this is a dimensionless combination. Okay. So this mapping, especially this one, will be relevant later when I discuss Lagrange expansion. Let me just mention it. I would consider Lagrange expansion with fixed Yamus couplings. So therefore, Lagrange essentially became a small alpha pi expansion. Very good. So with this quick introduction or motivation, now it became a bit more concrete. So I will remind you, I will introduce you the correlation function we would like to study. And I will discuss very briefly some properties, what's known. Then I will introduce, say, the main object of this talk, so-called integrated correlators. They are so-called first and second integrated correlator. And then I will finish with a conclusion and make some remarks. All right. So we want to study a four-point function of probably the simplest operator in N-for-superyamus, the superconformal primary operator with dimension 2. So they can be built out from the fundamental fields. Just remind you, N-for-superyamus has 6 scalars, where I run from 1 to 6 and transform under SO6 asymmetry. So this is essentially a symmetric traceless guy of these 2 scalars. So I remove the trace part because this is so-called the Konichi operator, which is not a BPS. So this particular combination has a half BPS and with a fixed conformal dimension 2. Okay? And another important point is that they are related to stress tensor and the supersymmetry transformation. So therefore, the correlation function, as I said earlier, is related to graviton scattering in superstring theory. People have considered much more general operators. I will mention briefly at the end, but this talk I will just focus on the simplest case. So this is well known that the 2 and the 3-point function of those half BPS operators are protected in the sense that they are independent coupling. So you can compute them just from field theory. The first non-trivial case, a 4-point function, which we will consider. Well, it's convenient just to remove the so-called free part, namely the part that you can compute it by free theory with contraction, and we will focus on the remaining one. But remember that this operator has many like ij index, which I didn't make it explicitly. So therefore, this 4-point function should have like many SO6 channels in principle. However, due to superconformal symmetry, all those different SO6 channels actually contained in this function, this I call R here, and for people from amplitude community, so this should be think of as delta Q. In fact, it's literally mapped to delta Q or type to be string theory. So then you're left with a single function, and this is the one we would like to consider. In literature, this is called a reduced correlator. So this function T, well, just like any 4-point function in conformal field theory, they are function of cross ratios called U and V, and they are functions of Yang-Mills coupling. I don't know if there are mathematicians there, but this may be not mathematically correct because it's a function of tau, but I just want to emphasize this is a non-holomorphic function. So I just put a tau bar as well. And so this is the object we would like to consider. As I said earlier, so this should be constrained under S duality. Okay. So before I discuss anything about the finite coupling, so let me just briefly give a very quick survey what's known. So people have developed extremely powerful methods to construct perturbative integrands, at least in the planar limit, for this 4-point function. I guess the record now is 12 loops, actually done by Jacob Bojali and Songhee group, Songhee who is from Beijing. Well, once you have integrand, you still need to do the integral. That's much harder, and the integral has only been done to 3 loops. Here, I just copy some answer from this paper, so by no means I want to tell you what this is. Just want to say this is a highly non-trivial object, even perturbatively. Okay? And then the strong coupling, so then you can use ADS-CFT correspondence by computing, say, Witten diagrams. In fact, the leading order in the strong coupling, which is supposed to correspond to supergravity limit, was done almost right after ADS-CFT was proposed by Mandasina. And then nowadays, people, of course, develop much more powerful methods, but there are still like limited results. Planar limit. Planar limit. Yeah, planar limit. Some of like for this like string collections, actually you can do finite coupling tau, but most of them, when I say, probably the first slide is all about the planar limit. Well, one loop will be, yeah, going to 1 over n. Okay, yeah. So as you probably get a sense that there's no way for me to compute this correlate at the finite coupling. I mean, perturbation, I only can, well, people have only, those are very strong, computationally very strong people, so they will only went to 3 loops. So I don't think I can do better. So rather, we will consider a simpler object, okay? And this has to be called the integrated correlator. Well, just from the name, so it's very clear what this means. So you just take the correlator, or rather this so-called reduced correlator, you integrate out the space-time dependence, okay? If you do so, then you're left with a function without the, depend on the cross ratio, you only depend on the coupling. But of course, you cannot just take the correlator integrate out the cost ratio, because any random choice of the measure, you either will get the divergence, for example, or even if you get a finite object, you don't know how to compute it. You still don't know how to compute it. So the point is that you have to choose the measure appropriately, which I will not tell you how to do it. But with these two choices of the measure, one called the first integral, the second integral called, well, I will comment briefly how this appears. And then the other way to compute this object exactly. Okay. All right. So the statement is the following. With that choice of the measure, these two integrated correlator are related to the partition function of N2 star super Yamnus, which is N4 super Yamnus defined by some master on the hypermodulary on S4 in following fashion. So first of all, maybe it's not so surprising that you take a 4 derivative on the partition function, so you naturally bring down 4 integrated operators. So therefore, it gives you the integrated 4-point function. But the point is that when you take a derivative, you bring down actually many kind of different operators. So the point of these two papers was to turn all those operators into using super conformal transformation to O2. And doing all those, and also I emphasize this is on S4, so you need to do a conformal. I want to compute the N-quadratic values on R4. So you need to do a conformal map to R4. So I have to collect all those contributions you led to those measures. Okay, but I will take it from here. So this relation, then why it's useful? Well, it's useful because famously that the partition function of N2 star super Yamnus can be computed from localization. So yeah, as I write here, so rather than a path integral, as shown by Preston, that the partition function is given by a finite dimensional integral. So let me just give you a little, well, I won't tell you exactly what are those objects. So the perturbative, well, essentially it's, sometimes people also write the Z1 loop. It's a one loop fluctuation around the fixed point. Then the instanton, sometimes also called the Nixon partition function. So gives so this gives you the perturbative contribution. This gives you the non-perturbative instanton contribution, which localize around the, say, north and south pole of the S4. So in principle, this is a finite dimension integral, so you can go and do it. Yeah, some of you may be expert on this topic. So this is not that easy. Well, especially I want to compute it for finite tau. Because I want to study, again, the S-duality. So any truncation of, say, number of instantons will not be SO to the invariant. I want to compute this for arbitrary number of instantons. And so just to remind you how, in particular, this Nixon partition function was computed. Well, roughly speaking, this was given by, say, if you want to compute a contribution of k instantons, you draw like a k box distribute in all possible ways, but I want the arbitrary k, so not the fixed number. Probably related to the first comment, that the properties like SL to Z, the modular property, is obvious. Well, it's very unclear. So we hope to do better. I will do this like case by case. So let me discuss the first case. I will call, yeah, people have to be called the first integral correlator, namely you take 4-point function, you integrate out with a certain measure. Well, I will really just start from the localization side. So namely, it's just two mass derivative of my partition function, or said another way, I expanded my partition function to the second order in mass, because I set the mass to 0 to go back to N4 triple. Sorry? M is the mass deformation. No, it's real. Yes, yes. So you add a mass term on the hypermultiplier. Yeah. Well, that's a factor so in the original paper of Nixoff, I don't know, this M, there was some confusion about this mass and the original, in the original paper of Nixoff. That was different by one. I don't know if that's what you had in mind. Um, yeah, so yeah, we can go on. Okay, so just assuming that, as I said, so this still looks very complicated, and the property is unclear. So I was thinking that if you expand that object in small mass to the second order, uh, without say deriving this formula, but I will sort of justify later, we claim that that rather complicated looking formula turns out it can be written in rather than n-dimensional integral, it's just one-dimensional integral. And maybe more importantly, that now the symmetry is manifest. So the coupling dependent tau only appears in this particular way. So with this little formula, and you can do a very simple calculation to check this is manifestly SO to the invariant. So again, for SUN, I expect to be SO to the invariant. And because the coupling dependence sort of trivialized, all the non-trivial information is contained in this function I call the BNT here. Yes, please. That's correct. It's only, yeah, so I will consider so-called a second integral correlator where you expand like a fourth mass order. That would be much more complicated. Yeah, that we will discuss that. Yeah, yeah. So as I was trying to emphasize, I don't know if mathematicians there, because it's a non-holomorphic modular invariant function. They are like infinity of non-holomorphic modular invariant functions. So this is a very special kind. I will actually comment on it. Okay. No problem. So yeah, so as I probably already said, that all the say sort of non-trivial information is contained in this function. I call the BNT. So in particular, you know, it contains all loop information and instant contribution. So here are just a few examples for SU2 and SU3. So you may already notice, well, the structure is very clear. So in fact, the numerator is always polynomial, and there's a fixed power. Because of that reason, there's an inversion symmetry. Namely, if you take t equal to minus t, 1 over t, it's invariant up to factor. There's another slightly more non-trivial property that this integrated to 0 if you put this measure. You may also notice this is in the form of Hilbert series. I should confess that I don't have deep understanding, but if you just take this object and you expand it in T and you Google it, so this actually counts the Vasily imbalance. So I didn't want to claim that I have understanding of this, but I just want to mention it. This one. Well, one is just you do it one by one, but later I will give you sort of generating function of this object. Then from there, in principle, you can just do the integral. You see this is yellow. There are sort of understanding from here, so you can try to do a Poisson Result. If you do the Poisson summation, you typically get that's where this square root of t came out. It requires this to be unchanged under Poisson summation, and that will appear. Then, yeah. Yeah. So since you asked, this property also related to. In fact, you can add any function which do not obey this condition, and that will integrate to 0. So in principle. Anyway, so let me move on. So, I have this t integral to do. One way to do it, I just Taylor expand this object. Then I integrate it one by one. Okay? Well, it's very clear what you will get. So, roughly speaking, you will get something like this. And this ES is a so-called non-holomorphic Einstein series. Yeah, so indeed, so I expand in T, then you do the integral. That's basically the definition of the non-holomorphic Einstein series. This infinite sum is formal, so namely it's not convergent sum, but you can easily make it convergent by writing this as a contour integral along the imaginary line. Okay? The second line is just sort of rewriting, but now this is well defined. For those who are familiar with the SO to Z spectrum decomposition, immediately recognize that this is SO to Z decomposition for this object. Namely, so let me just remind you, any modular invariant function can be written as a constant and a continuous spectrum, namely non-holomorphic Einstein series, and discrete spectrum, so-called mathcal form. So here, the statement is that for this object, there is no mathcal form contribution. So this is sort of related to your question. In general, you would have this, for example, for the so-called second integral correlator, there will be, if I do the spectrum decomposition, there will be non-trivial mathcal form. And mathcal form is much more complicated than a non-holomorphic Einstein series. So this is an extremely simple modular invariant function. So I didn't give you an expression for this BNT. I just gave you a couple examples. Well, because one can do better, just give you a generating function. So one can actually sum over all the SUN, and if we do the sum, we were able to actually derive this formula by making a connection with a Hermitian matrix model. But anyway, the result is this generating function, which now from here you can of course expand in Z to read off any BN you wish. Another useful property coming out from this generating function is that turns out this obey second order differential equation on T and Z. So second order derivative on Z, if I translate it into integrated correlator, it becomes difference on N. Right? And the differential T, if I do an integration by part, it can be translated into derivative on tau. Collect everything together, you will find that this integrated correlator actually obey what we call the Laplace difference equation. So this is a Laplace operator on the upper hyperbolic plane. So this, in some sense, gives you an extremely efficient way to compute the integrated correlator because there's a relation coming from, say, if you start from SO2, then you can recursively compute the SO1. Another use from the generating function is that it streamlines the Lagrange expansion. So almost by definition, the the Cn can be written as counter integral around z equal to 0. Now you can deform the counter, as you may notice that this function has some cards. So pick up cards and do a set point. You will find that in the Lagrange expansion with fixed Yang-Mills coupling, the integral correlator takes this form. As I emphasized before, so with fixed Yang-Mills coupling, one-way expansion is essentially alpha pi expansion in string theory. So therefore, the leading guy is a supergravity contribution. And indeed, so if you take the known supergravity amplitude, you do the integral, you will find exactly, say, 1/4. Those one-way collections, as I said, translated into string theory, they are alpha pi collections. So for example, in the leading order, if you plug in all the numbers, you will see E3 half. So essentially those are 0. And that's exactly what you expected because Green and his cooperator already derived, in flat space, derived the Wilson coefficient for r to the 4. And if you go on, say d4 r to the 4, you see E5 half, and so on. The second line, as I said, I use a different notation. So in fact, you need a new modular function, which I got d here. And d is defined in this way. So if you forget the exponential decay part, this part is more or less the same. Well, it's basically the same as a non-holomorphic Einstein series. But this is exponential decay when you take n to be large. So let me be quick. So the statement is that the first line, as expansion in 1 over n, actually, it's not Bohr-sumable. So this is asymptotic theory in 1 over n. And for this to make sense, you need an exponential decay term. This can be made precise, actually, when you did it. You literally can do a researching analysis to derive this exponential decay term. Once you have result in tau, you can translate it into any other coupling. Well, in particular, you can translate into, say, more familiar de Hooft coupling. So in the de Hooft coupling, this exponential decay term essentially becomes, say, square root of lambda. So this is exponential decay in large, in strong coupling. And the Einstein theory, which I didn't really tell you, but you trust me, if you translate into lambda, it just becomes 1 over lambda expansion. So again, the first line became 1 over lambda expansion, and the second line became exponentially decay. And these two are again related to each other. So resurgent in the sense that this power theory is not Bohr-sumable. Yeah, so this can be interpreted as the area of the bigger string if you translate it into a string language. But there was no concrete calculation. Right? Here I'm just doing translation. Okay, so let me move on to discuss still the so-called first integrate correlator, but for more generic gauge group. Okay, so yeah, SO2 engaged group, which is a simple list group. So therefore, this is very much similar to SUN. And indeed, so we found the result is, well, basically the same, except this what I call the BT here before. It changed a little bit. So here I give you two examples just to show you, say, the group relation you expected also reflecting in this result. For SO2n plus 1 or USP2n, it became more interesting. And the S transformation now became, rather than say, there's a factor 2. Okay, rather than just minus 1 over tau, but 2 tau. And the statement that the integrated correlator we claim should take this form, and we of course confirmed. So what is the point? The first bit is basically the same as what you saw before. The second part, which is new, well, looks similar, but the change is that you basically rescale tau by 2 tau. And this factor 2 is, of course, related to this 2. And with this expression, one can show that this is not S02 invariant anymore, but it's invariant under the gamma 02, the congruous double group of S02, which is generated by T and S hat. No. Yeah. So yeah, also previously it was not sensitive to SUN and UN. Right. So S duality says more that under S transformation, these two qualities are supposed to exchange. So if you do a little calculation, you will notice that if you do this transformation, essentially these two exponents exchange. Therefore, for that to happen, so you really require the coefficient between these two gauge group exchange, namely this relation should hold. And yeah, indeed, so we computed those coefficients for localization, and that's exactly what happens. So let me just skip they also have very similar Laplace difference equations. Let me just skip this part and move on to the so-called second integrate correlator. So again, we are computing the same correlator, but with a different integration measure. But from, say, localization point of view, now I'm expanding the partition function to 4 mass order. Okay. Well, turns out this object is much more difficult, as I mentioned earlier. But the main difficulty is the Kronecker partition function. Once again, I want the average number of instantons, not the 1 or 2 instantons. So there is no known result for finite n, like I discussed earlier for this object. What has to be understood is in the Lagrange expansion. And you will already see that in the Lagrange expansion, this object is much more complicated than the previous one, or in some sense much richer if you want. Okay, so this talk I will just focus on Lagrange, but fixed tau. Yeah, as I discussed before, so with fixed Yanu's coupling, one-way expansion is essentially alpha pi expansion in string theory. So the first term, the leading in M, again, is the supergravity contribution. The coefficient changed because the measure changed. Then more non-trivial part, namely, which depend on the coupling. So it turns out, unlike the first case, you may or may not remember that the expansion for the Lagrange expansion for the first integrate correlator was always in the form of half integer power in 1 over n. But in this case, we have both half integer and integer power. And for the half integer power, which I write here, is basically very much similar to the first integrate correlator. So at each order, say the coefficient is given by linear combination of the so-called non-holomorphic Einstein series. So very similar. And in fact, we know this to any order because we actually found that there's a recursion relation related different orders. Good. So therefore, this talk will focus on the integer power part. Okay. Here, just the first few orders in the one-way expansion with fixed tau. The first guy, again, in the interpretation, if you do a sort of power counting, the interpretation is a supergravity, but at 1 loop order. And I mentioned that the 1 loop order, the answer is known. So indeed, you can take the answer, do the integral. But in this case, the integral is much difficult to do. But nevertheless, you can do it numerically, and you find indeed agree with the localization. what I really want to focus on is those higher order ones, which has a non-trivial depend on the coupling. In the first say collection to the one loop supergravity, by power counting, it corresponds to D6 R to the 4. In the flat space, this Wilson coefficient of D6 R to the 4 was worked out by Green and Van Hall. And using supersymmetry and so on, they found this coefficient is given by something called the generalized isosceles. Michael Green once told me that the mathematician Don Zagier was complaining this name because anything except the isosceles can be called the generalized isosceles. But they didn't come up with a better name. Anyway, so I will follow in what the. Sorry? Okay. I don't know. Okay, I can ask you later. Okay. Well, there's a precise mathematical definition is given here. So they are defined by this equation. So they are, say, modular invariant solution to this equation with appropriate boundary condition. And the boundary condition is set up basically by tree-level string theory. Okay. Anyway, so this is called the generalized isosceles. And just as a comparison, the non-holomorphic isosceles obey very similar equation, except there's no say source term. Yes, please. I will come to that. So yeah. I will spend a lot. I thought that there would be some mathematics. So I prepare a lot of mathematics. So, but anyway, yeah, there's a lot of discussion on this object. So it turns out solving this equation is much more complicated compared to your question. That's actually why they need a Stephen Miller. So Stephen Miller is an expert of modular function. Actually, he was one of the authors of solving this sphere packing in 24 dimensions. Anyway, so in that paper, they will try to just solve this equation for this very particular case. Okay, like s equal to 4 as well as. Let me spend more time on this generalized isosceles. Then we did so in this paper with Stephen Miller, so they loaded the solution as usual. You know, you have a differential equation, so you write as a so-called special solution and the homogeneous solution. So there's a special solution, there's a homogeneous solution. Then we did the localization computation. We sort of see that the so-called homogeneous solution in their paper should be 0. So I should also mention, although I didn't write out here, I should also mention the special solution they loaded out was extremely complicated. It's like an infinite sum or like 2 divisor sum, product of the divisor sum. So that's why it's highly non-trivial to see it's 0. We did it numerically, we found indeed it's 0. And then we made a conjecture. Then mathematicians, including Stephen Miller and others, tried to prove it. So the most recent statement is this paper. Radichenko actually also was in the paper on this 24-dimensional sphere packing problem. So anyway, so the statement now is that this generalized isosceles can be written as a special solution, which I will not tell you what it is, and some homogeneous solution. And our conjecture was correct or incorrect in some sense, because as you can see now, the special solution is given by sum over holomorphic classical forms, or 2s. You may know the statement that there is no holomorphic classical forms before weight 12. So in the case where we made the conjecture was s equal to 4. So it was 0 just because there's no holomorphic classical form. Right. Generally, that equation has homogeneous solution. You may also question, which one I call the special solution, which one I call the homogeneous solution is ambiguous. So what do I mean? Well, in this case, it turns out that there's a well separation because this coefficient, which I haven't tell you, contains L values. So this has rich, say, number theory properties. And so this is essentially, what we do is that essentially you put all the, say, L value dependence into what I call the homogeneous solution. So therefore, there's a very well-defined separation. Good. So I should also say that all my discussion is only for integer s and integer or half integer s1, s2. So mathematicians are still working on this to try to understand better, say, for more generic those parameters. So in summary, so this is a much more complicated object, unlike the Einstein series. Just to give you some intuition, so this object in the physics language contains the so-called instanton and anti-instanton pairs, like have QQ patterns. But Einstein theory only has instanton and anti-instanton separate. Good. So now I have a general solution, so I can just plug in, say, this solution into localization result for the integrated correlator. I just want to focus on this homogeneous solution part. So as I said, this become non-trivial only if S bigger or equal than 6. So let me take the first non-trivial case, namely S equal to 6. The localization result takes this form, and alpha, beta, gamma are some rational numbers which we determined from localization computation. So yeah, so we took this solution, especially the homogeneous part, and we plugged in. We found remarkably that those homogeneous solutions, although has very interesting number theory properties, they actually cancel out exactly. And we found a similar cancellation in the higher order as well. So this is suggesting that the non-holomorphic Einstein series probably is not the best basis for describing what we call the secondary integrated correlator. Rather, you want a new basis, which are linear combination of the generalized Einstein series. And this new basis, where the L values or Casper forms cancel out exactly. Okay? This is a non-trivial mathematical problem. However, there's a solution. And the solution is that any such object turns out has a lattice sum representation. So this formula now looks familiar compared to what I discussed in the earlier part of the talk, namely the first integral correlator. So just slightly more difficult, or more complicated. So rather than one-dimensional integral, now integrate over, say, 3 parameters. And rather than one dimension, you sum over 2 integers, now you basically sum over 4 integers. So the constraint. But the point is that the tau dependence always appears in this particular way, and the only non-trivial information is contained in this function I call the B again. And essentially, one needed to construct this B so that the resulting function is modularly invariant, and they are the linear combination of the generalized Einstein series free of Casper form. And such construction was provided actually by Don Zagi. And so with that, it implies that there's an analog to the first integral correlator that at least in the Lagrange expansion, we also have so-called lattice sum representation for the second integral correlator. But we don't know the story at the final end, as I said. All right, so let me summarize. I think it's remarkable that one can actually compute correlation function, well, also not correlation function, but integrated correlator, exactly using, in this case, using supersymmetrical localization, but I want to emphasize, very importantly, also using the mathematics of modularity. So in this talk, I discussed the so-called first integrated correlator with generic classical gauge group. People also work out exceptional groups. And then the so-called second integrated correlator, which is much more complicated. So this talk, I only focus on large N expansion. With those so-called integrated correlator constraints, one can combine with other approach, in particular, say, analytic or numeric bootstrap. You can reconstruct the correlator itself, at least maybe in large N expansion, or numerically put a bound on non-PPS operators, as say Schweitzer did in his talk. So finally, I just want to mention that in this talk, I have only considered probably the simplest four-point function. One may consider more generic half of PPS operators. But turns out, for such generic case, there is no known localization computation. Well, people don't know how to compute or define the, say, integrated correlators that can be computed from localization. Another possibility is to consider a four-point function of this form, where two of the operators is still O2, and the other two operators can be general, and maybe you can also set the dimension of the other two operators to be very heavy or large charge. Such four-point function can be considered as a two-point function in the background that is generated by this two heavy object. So there's such object often called the heavy light correlators. They're very interesting study on this. So for example, you can take this operator has a dimension n, namely, say, joint graviton. So in that case, this four-point function can be considered as a two-point function scattering of a D-shaped ring, because the joint graviton is dual to a D-shaped ring. One can also consider a higher point function by inserting some other operators. In this case, L is Cairo-Lagrangian. They are dual to axion dilaton in string theory. In that case, this correlator is not a modular invariant. Rather, it has a non-trivial modular weight. One may also consider with non-local operators. So, say, light defect. In enforcer-Bianus, you have, for example, Wilson lie or the Haupt lie, and they are related under, say, inversion. So therefore, this two-point function in the presence of lie should be transformed, again, according to S-duality in a non-trivial way. People have also studied, say, correlators in lower supersymmetrical theory. I think with that, finish, and thank you for attention.
Audience.
So this introducing mass parameter and taking derivative to obtain integrated correlator. I heard this story also in 3D, and in 3D case, if you consider square sphere, you can consider new correlator. So I wonder whether you can do it in 4D, maybe ellipsoid.
Right. So you mean take a derivative with respect to the squash B?
Yeah. So you first have to generate this localization formula to ellipsoid. And
take that's right. You can do that. So from the, I don't know if there's a formula I need to point, but maybe. So from the localization computation, actually in the paper, maybe one of the reference, we show that taking B derivative, there's no difference. There's a linear combination of what's already done here.
Oh, yes.
But you may ask if you get the independent integration measure. yeah, I know Silvio Pufu and Strachester work on this. The claim is that there is no new constraint.
Oh, I see.
Yeah.
Thank you.
No problem.
Any other questions? So maybe I can ask a very naive question. So this related defects, thinking of maybe like topological line defects, perhaps, or something more general.
Here, so I'm more, more specific, just version line, half of PBS. Well, more generally, you can charge the dionically with the PQ charge. So as I mentioned, under S duality, the version line is mapped to hold line. So therefore, this object, unlike the one I discussed earlier, transforms non-trivially. So you have to construct the automorphic function, yeah, with that transformation.
Okay.
That's what had to be studied in the literature.
That's interesting.
Hi.
Yes, so I'm going to ask you the same question I asked you 3 years ago at Queen Mary. But maybe now there is some understanding of this. So there is this holomorphic anomaly equation that certain coefficients or higher curvature terms in the supergravity action satisfy. It's a derivative with respect to the modular parameter. So you have this, I think you are looking at some R to the 4 coupling, and there is an holomorphic element equation that the generalized Eisenstein series satisfies. And so, well, we know from Marco's talk yesterday the coefficients of this couplings have some interesting meaning. Like they are counting instantons or something. If you expand it in power series, like what probably you are doing. So is there anything that we can understand from the coefficients of the series at this time, or is it still a bit mysterious?
So which coefficient you refer to? You mean coefficient R to the 4, D4 to the 4, or you mean?
So you have a formula for the generalized Eisenstein function.
So I have a formula for generalized. I didn't write it down, so yeah, but there is a perturbative expansion for generalized answer.
Yeah, so you have some homogeneous and an inhomogeneous solution.
Oh, yeah, so there's a homogeneous, yes.
Yes, so this function, I presume you know it by some approximation or some power series or something like that.
Yeah, okay. Yeah, okay. So, right, so, yeah, unfortunately, I didn't write down any formula. So indeed, so this, like any, say, modular invariant function, so you can do so-called Fourier mode decomposition, or in the language of physics, you can expand in 0 instanton, 1 instanton, 2 instanton, and so on.
Right.
So 0 instanton is a perturbation, as you said. Interestingly, this guy, perturbation actually truncates, has only 4 terms. So in the string theory language, it's like a genus 0, genus 1, genus 2, genus 3. Then there's as I mentioned actually, there's like a QQ pattern, so namely exponentially decay term.
I see.
So indeed, the people show that even though you only have 4 terms, it's like a polynomial, there's no issue about the convergence. But there's something called the chit-chat cat. Is it called chit-chat cat in the Wonderland, Alice Wonderland? Chit-chat cat resurgence. So the point is that this truncated perturbation theory is due to some sort of extant symmetry. So what the people did is sort of deform say this function a little bit, so that you get the asymptotic not Boole-Stangable theory, and then you can go through this Boole summation, and indeed you can relate like power theory with exponential decay.
Is there an
I can give you
understanding?
more details.
So why exactly it truncates again? Maybe I missed that part.
Well, so first of all, the Einstein theory, if you do this expansion into perturbation and the instanton, so Einstein theory actually only has two perturbative terms. Roughly speaking, when you plug it into that and try to solve it, you may more or less see that this only has like a few truncated perturbative terms. So this was caused by the fact that the source term has a truncated.
Thank you.
Hey, any other questions? We got like 10 minutes. Okay, if not, then let's thank the speaker again.